Let's solve some calculus problems about the derivative as an instantaneous rate of change. The first problem says the temperature T, capital T, in degrees Fahrenheit of a cold yam placed in a hot oven is given by this function, capital T equals f of little t. I'm using little t for time in minutes and capital T for temperature. That might be a little confusing, but it's also kind of fun, you might say. Part A says, what is the sign of that capital F prime of t, the derivative of f at t and y? Okay, I hope that one is pretty clear. The yam is cold, it's in the oven, so it's warming up. The graph of capital T, the temperature, as a function of little t time is increasing. The slopes of tangent lines are positive, therefore capital F prime of t is positive, okay? And I gave you a verbal explanation as to the why. We could just say slopes of tangents are positive. Slopes of tangents are positive. You could also say capital T is an increasing function of little t, though there are some exceptions in that case where the derivative can be 0 at isolated spots. Don't worry about that too much. I'll just say slopes of tangents are positive. Again, capital T is an increasing function of little t. It might be helpful to graph capital T as a function of little t here, a plausible kind of graph. You got to be careful here. You got to think about the temperature of the oven as being a horizontal asymptote for this graph. If the yam is cold to begin with and it's put in a really hot oven, it's going to warm up very rapidly at first. The slope of the graph will be very large. Capital F prime of t will not only be positive, but will be large. However, over time, as you approach the temperature of the oven, the graph will level out. The derivative will get closer and closer to 0. Still positive, but closer and closer to 0. This graph is concave down. It is approaching this line as a horizontal asymptote. But we don't need to know the formula in this problem. We just need to think about this qualitatively. Part B says, what are the units of what you see in this equation, f prime of 20 equals 2? Ultimately, what are the units of the 2? And what is the meaning of this statement? Let's go ahead and think about that. It's helpful for this kind of situation to think about Leibniz notation for the derivative. F prime of 20 could also be written as dt dt in this case. That's kind of fun. dt dt. The derivative of capital T, the dependent variable, with respect to little t, the independent variable. That's helpful because what you often do in calculus is you pretend this is a fraction. Now, technically, it's not a fraction. It's the limit of fractions, limit of ratios. So technically speaking, it's not. However, pretending it's a fraction often is a useful thing to do. And in this case, it's useful for determining the units because if you pretend it's a fraction, the units would be the units of capital T per unit of the little t. This would be in degrees Fahrenheit per minute. We should specify that little t is evaluated. This is evaluated at little t equals 20. That's done by putting a vertical line and a little t equals 20 down there. And this equals 2. The units of capital T are degrees Fahrenheit. The units of little t are minutes. So this is 2 degrees Fahrenheit per minute. Okay? Let me just verbally say the meaning of this statement, and I'll expand on that in part C when we approximate f of 22. So this is saying, well, I will say this is the rate of change, instantaneous rate of change if you want to be more specific, of temperature with respect to time when you are at time 20 minutes. At time 20 minutes. So 20 minutes after you put the yam in the oven. It's not rising in temperature very rapidly because this is positive, though small. You know, initially the rate of change might be more like 20 degrees Fahrenheit per minute or something like that. Let's expand on the meaning of this for part C. Part C says approximate f of 22 if you know f of 20 is 150. That's called a linear approximation is what we're going to use here because we don't have a formula for f of t. So we're thinking about the graph here. Imagine this is time 20 right there. The value of the derivative, f prime of 20 equaling 2, tells you the slope of the tangent line to the graph at that point, which is the best linear approximation to the graph at that point. If you zoom in closer and closer to that point, it will look more and more like its tangent line. The value of the function there is 150, and the slope of this line, slope equals 2. We're going to use that line to approximate the function. In other words, we need to find the equation of that line effectively, plug in 22 into that equation. We will get a value on the tangent line that's going to be a little bit too big because the green graph of f of t is concave down. The tangent line is above it, okay? But we don't really worry about that too much. Let's just go ahead and do it here. There's a couple ways you could write this. You could say f of 22 is approximately f of 20 plus f prime of 20 times 22 minus 20. Now, where in the world did I get that, you might be wondering. Effectively, I'm using the point slope form of the equation of the tangent line when I write that. If you want, you could write y equals L of x equals f of 20 plus f prime of 20 times x minus 20 as the equation of a function whose graph is the tangent line. There's your slope. It gets multiplied by x. F prime of 20 is the slope. And yes, when x is 20, this part's 0, and you get f of 20. L of 20 equals f of 20. It goes through the right point. All I did in going from here to here is just plugged in x equals 22, but I didn't say that when I first wrote this down. Anyway, using the numbers that were given, f of 20 is 150, f prime of 20 is 2. This becomes 150 plus 2 times 22 minus 20 is 2. The temperature went up by 2 times 2, or 4 degrees Fahrenheit. The final temperature, our approximation, is 154 degrees Fahrenheit. Again, that's probably going to be a little bit too big because this graph is concave down. Another way you could write the answer, or to think about approximating f of 22, that's perhaps a little bit more intuitive, is to think about it in terms of the rate of change, the derivative, as telling you the approximate change in y. This is a delta y here. That's not a triangle. That's a capital Greek letter, delta. Delta y is approximately the rate of change at 20. I'll go ahead and use the Leibniz notation for that. dt, capital T, d little t, evaluated at t equals 20, times delta little t. I guess I shouldn't have called that delta y, should I? I should call this delta capital T there. I will leave that as a y, but don't worry about it. The change in temperature is approximated by the rate of change times the time elapsed. So this is therefore 2 times 2. This is 4. This is telling us we would approximate the change in the temperature to be 4 degrees Fahrenheit. It is positive. It's going up. It's heating up. And that's what we found. The temperature went up from 150 to 154. I now use that to say the final answer is, once again, 154 degrees Fahrenheit. Okay? But again, that's going to be a little bit too big. If it was a hot yam and you put it in the fridge so it was cooling down, what would happen? The graph would be decreasing in concave up. It would approach a horizontal asymptote still. The derivative would be negative. The rate of change of temperature with respect to time would be negative. We would expect the temperature to go down over a small amount of time. Number 2 is about investing, though with kind of a strange twist to it. Investing $1,000 at an annual interest rate of R%, compounded continuously, for 10 years gives you a balance, B dollars, where B is a function of R. The twist here is that we're thinking of the balance as a function of the interest rate, not of the amount of time that's gone by. We're specifying the amount of time to be 10 years. Our goal is to give financial interpretations of some statements and then use a linear approximation at the end. Part A says G of 5 equals 1,649. No calculus there, that's just interpreting the meaning of the function. Part A, when R is 5%, 0.05 as a decimal, the balance on the account after 10 years is $1,649. I'll go ahead and write that down. When the interest rate is 5%, if you were using the compound interest formula, you'd plug it in as 0.05, but here we write 5%. the balance in the account after 10 years is $1,649. Okay, that's just a statement about the meaning of the function itself. Part B is about the derivative. G prime of 5 equals 165. Once again, let's use Leibniz notation to emphasize the units. G prime of 5, the rate of change of the balance with respect to the interest rate, we could write dB dr, evaluated at r equals 5, is 165. Okay, so let's go ahead and write out what this means. This means, and we can also answer the units of G prime of 5. The units, let's go ahead and write the units first. It would be units of B per unit of R. B is in dollars, R is in percent? Yeah. You could say this is in dollars per, you don't say percent here, you would say percentage point. Kind of a weird thing, but it is standard. Percentage point. Intuitively meaning, this is a rate of change of B with respect to R. For every percentage point increase from 5% here, like from 5 to 6%, you would expect the final balance to go up by about $165. Okay? It is a linear approximation. When you say that, the graph is not necessarily going to be straight here. That's how you would interpret this. Let's go ahead and expand on that. This is when the interest rate is 5%, the rate of change, I'll abbreviate now, rate of change of B with respect to R is $165 per percentage point. So let's go ahead and just pretend the interest rate increases by 1 percentage point. If R increases by 1 percentage point, the reason you don't want to say percent here is because it can be misleading. If it increases by 1 percentage point from 5% to 6%, because if you just say it increases by 1%, 1% of 5 is 0.05, and then you could misinterpret and think you're going increasing from 5% to 5.05%. So we want to increase by 1 percentage point. That is standard terminology for increasing this from 5% to 6% or 3% to 4%. The balance, the final balance, will increase by about $165. Okay, will that be exactly right? Probably not. Let's think about what the balance graph would look like as a function of the interest rate. Maybe you have intuition for this, maybe you don't. Actually, you know the balance as a function of time t is exponential growth, increasing concave up. Is the balance also an exponential function of r? It turns out it is, though maybe that's not intuitive to you. It still is an exponential growth function and still increasing concave up. I will write down a formula for the balance as a function of r here, but to emphasize that, but not right at the moment. I'll do that at the very end. And so if we're using a linear approximation here, it's concave up, the tangent line is going to be under the graph. It's actually going to go up by a little bit more than $165. This will be an underestimate. In part C, we're actually using a linear approximation to estimate g of 6. I sort of did that verbally already. How does this compare with the true value of g of 6? I did that verbally already. So g of 6, well, let's think about it in terms of change. Change in the balance is going to be approximated by the rate of change, dB dr, when r is 5 times the change in r. So if the change in r is 1, because we're increasing from 5% to 6%, and we know the derivative is 165, this is going to be $165 per percentage point, which I'll abbreviate like that. times 1 percentage point. PT means point. Giving you $165. The percentage points cancel. The change is $165. That's not the final answer, though, because we need to estimate g of 6 itself. Therefore, g of 6 itself is approximately g of 5 plus 165. G of 5 was 1,649. 1,649 plus 165, I'll do that in my head, that would be $1,814. That would be our linear approximation. Again, because the graph's concave up, it's going to be a little bit too small. What's the actual answer? Can we come up with a formula here? The balance is a function of R. Thinking about the compound interest formula with continuous compounding, you'd put the initial balance there, 1,000, times E, you'd use the number E when you're doing continuous compounding, to the, what is the interest rate? It's 5%. Well, in general, it's R%, excuse me. But to use the formula, you have to divide by 100. You have to get rid of the percent sign and convert to a decimal. We're doing it for 10 years. The amount of time is 10 years. We could write R over 100 times 10. There's the interest rate converted to a decimal. 5% would get converted to 0.05. 6% would get converted to 0.06. There's the amount of time that's elapsed. This does simplify to 1,000 e to the 0.1 times r, and that is exponential growth. It will be increasing in concave up. And we also can plug in r equals 6 here to see that this answer is going to be a little too small. A more precise answer would be 1,000 times e to the 0.1 times 6 is 0.6 power. 1,822 is more accurate. Yes, we were a little too small. Number 3, you can see, is about fuel efficiency, and it is a little confusing. You got to really be careful in thinking about this one. G of V is the fuel efficiency in miles per gallon of a car going at V miles per hour. So V is the speed, and G of V is the fuel efficiency. I have not specified a variable here for the fuel efficiency. Let's go ahead and do that. If you're not told a variable, you can also make up your own variable, maybe capital E for efficiency or something like that. Could be a variable name that you give to this. You want to imagine that you're going at a constant speed here. You want to imagine V is in miles per hour and you hit the cruise control. All right? It's not that you can't change your speed. Obviously, you have to speed up and slow down when you're driving. But in thinking about this function for any particular value of V, you want to imagine you are on cruise control. What are the units of G prime 70? What is this practical meaning in terms of this statement right there? Okay. All right. Once again, think about Leibniz notation. G prime of 70. If you've got a variable that you're calling the dependent variable, I'm calling it capital E here. In Leibniz notation would be dE dV, the rate of change of the fuel efficiency with respect to velocity, speed, effectively. We could imagine we're just going in one direction. Evaluated when you are going 70 miles per hour, that is negative 0.54. I'm going to be answering both questions here at the same time. Units would be units of E per unit of V. This is where it gets confusing. Units of fuel efficiency are miles per gallon. Units of speed are miles per hour. The units of this would be miles per gallon per mile per hour, and I think it's a bad idea to cancel the miles. Yes, you could, and yes, you could say the units officially simplify to hours per gallon, but that's kind of confusing. More importantly, it's more important to leave it like this to help you interpret the practical meaning of it. And what is the practical meaning? Therefore, when you are going at V equals 70 miles per hour, 70 miles per hour, the rate of change, ROC, of fuel efficiency with respect to speed is what you see there, negative 0.54 miles per gallon per mile per hour. Now, we're not asked for any linear approximations here, but I think it's a good idea to expand on the meaning of the rate of change by giving effectively a linear approximation. Therefore, if the speed is increased by 1 mile per hour, say, from 70 miles per hour to 71 miles per hour, you had the cruise control set at 70 for a while, you decided to up it by 1 mile per hour to 71 miles per hour, and now you are cruising at that speed. The fuel efficiency, let's go ahead and phrase it like this. You could say it will change by negative 0.54 miles per gallon, but you also could say will go down by positive 0.54 miles per gallon. It will go down. The change will be negative. You're getting less fuel efficiency. You're being less efficient. But you could also say, like I did here, it will go down. It will decrease, I could have said, by 0.54 miles per gallon. And if it increased by 2 miles per hour from 70 to 72, you'd multiply this by 2 to estimate how much it would go down. Is it always going to be negative in this kind of problem? Let's just imagine what the graph of G of E might look like here. Capital E, the fuel efficiency as a function of the speed. If you are going 0 miles per hour, if you're not moving, but the car's on, the fuel efficiency is 0. You're getting 0 miles per gallon. It's bad when you are going slow, and it stays bad if you're even going 1 mile per hour or something like that. You're being inefficient. It's going to get more and more efficient. It's going to be positive for a while, the derivative. E will be an increasing function of E. Will be concave up or concave down, I'm not so sure. You'd probably have to do experiments. There will be some sort of optimal speed here where your fuel efficiency is highest. If you go too fast, it becomes less efficient. The derivative does eventually become negative. Probably has some sort of, the v-axis is a horizontal asymptote. There's some speed that is the ideal speed for fuel efficiency. Ideal speed. For fuel efficiency, that might not be a practical speed on the freeway, right? It might be too slow, and people would be honking at you and that kind of thing. It also if it's too slow, it increases the time it takes you to get there, and that could ultimately still mean you use more gallons. But as far as miles per gallon goes, that's your ideal speed for maximal fuel efficiency. And this is what happens in reality. Our last problem is about revenue from car sales, capital R in thousands of dollars, as a function of advertising expenditure A in thousands of dollars. So this is confusing here because the units of both R and A are thousands of dollars. When you interpret the derivative as a rate of change, it's going to be good to add the phrases like with R, thousands of dollars of revenue, and with A, thousands of dollars of advertising. That'll help us interpret it. Part A says, what does the company hope is true about the sign of the derivative, f prime of R? You would hope that as you spend money on advertising, certainly that derivative is positive, that at a very minimum. We hope f prime as a function of A is positive, meaning the rate of change of the revenue with respect to advertising dollars is positive, meaning the graph of R with respect to A is increasing. You've got positive slopes. As you spend more in advertising, you're going to get more revenue. That's a minimal hope. It's not necessarily as good as can be, though, as we will see in this problem. Revenue is different than profit. Revenue is just how much money you're taking in. Profit is revenue, you ignore costs. With profit, you got to think about costs. It's not just how much money you're taking in. It's the amount of money you're taking in minus your costs. Profit can easily be negative when the revenue is positive because your costs could be too big. And here we are thinking about costs. We are thinking about advertising expenditure, which is a cost. That's going to be relevant for later in this problem. But that's certainly a minimal hope for part A. And you could, if you were asked to explain, you could say, well, certainly we would not want the revenue to go down as we spend more on advertising. That would be terrible. Part B, what does the statement f prime of 100 equals 2 means in practical terms, and how about f prime of 100 equals 0.5? Well, these are rate of change statements. They are derivative statements. F prime of 100, using Leibniz notation, would be dr dA, evaluated at a equals 100, and it is 2 here. This would be, let's go ahead and use units, $1,000 of revenue per $1,000 of advertising. That is a rate of change. I'm not going to write out what it means in practical terms to save time. I'll just explain. This is a rate of change of the revenue with respect to the advertising expenditure. When the advertising expenditure is $100,000, A is 100 means $100,000 of advertising. That rate of change is $2,000 of revenue per $1,000 of advertising. So if A increases by about $1,000, say, meaning delta A is 1, you can expect the revenue to go up by about $2,000, 2 times 1. If f prime of 100 equals 0.5, the units are the same, and the big idea of the interpretation is the same. It's just the value that's different. So here we're saying if you're currently spending $100,000 on advertising, the rate of change is $0.5 thousand of revenue per $1,000 of advertising. So if the advertising budget goes up by $1,000, delta A is 1, from 100 to 101, we could expect the revenue to go up by about $0.5 thousand. Less increase of revenue compared to the increase of advertising. So you're actually gaining money in this case. Your profit is increasing, but losing money in this case, even though it's positive. Your profit would be decreasing because your advertising budget is going up faster than your revenue is going up. And that's elaborated on for part C. Suppose the company plans to spend about $100,000 on advertising. That's the current plan, at least. If f prime of 100 is 2, should the company spend more or less than 100,000? Should they increase their advertising budget or not? And what if it's 0.5? Essentially, I've already answered this verbally, and I'm not going to bother writing it down to save time. Let me emphasize the meaning verbally again. If f prime of 100 is 2, I'll go ahead and say the answer. They should spend more on advertising for that first part. Okay, more when f prime of 100 is 2, which is bigger than 1. That's the key thing, not just bigger than 0, but bigger than 1. They should spend more because they would expect their revenue to go up by about $2,000 when they only spend $1,000 more on advertising. Okay, based on the fact that the rate of change of R with respect to A is 2, it's bigger than 1. You should spend less on advertising, only 2 S's and less when f prime of 100 is 0.5, which while it's still positive, it's less than 1. 1 is the key boundary here. That being less than 1 means you would expect to gain less in revenue for each extra dollar of advertising. You could expect the revenue to go up by about $0.5 thousand, about $500, if you increase your advertising budget by about $1,000. So this is a little trickier than just whether the derivative is positive or negative. You got to really think about what's going on in real life here. Thanks for watching.